So here, ma'am, I am truly honored and glad to share the same stage with you. We want many things from you, and we are really appreciate your presence. So ladies and gentlemen, can we have the very big round of applause for this inspiring lady who are here with us. And I think we totally, ma'am, honored to have you here tonight. Thank you. Over to you, ma'am.
Thank you so much. Good evening, Kolkata. Very happy to be here. Thanks to Tata Steel, Tiscon, and Deson for organizing this wonderful event. I was not very sure if I was coming to this, but Sajalji and Divyenduji have put a lot of pressure for my good. I'm enjoying the event. Finally, I'm here. And most of the talks were in Bengali, but I could follow because it's the language of civil engineers. I will be talking in English, try to make it very simple. Though I am not from Bengal or I'm not associated with Tata Steel directly, there's so much connection between us. I'll tell you why. The founder of Tata Group and founder of Indian Institute of Science is the same person. Is none other than J.N. Tata. So that is why our institute is called Tata Institute. If you go to Bangalore, if you take an auto or taxi, you cannot say Indian Institute of Science. You should say Tata Institute. And our institute has this big founder statue in front of the main building, an iconic J.N. Tata holding the replica of IISc. And the formation of IISc also has a story. J.N. Tata was traveling in a ship to Chicago on his business, and he met a Bengali. Can you guess who it is? Swami Vivekananda, right? And that is the time Vivekananda told Tataji that, see, why are you traveling to other countries for all this? We should have our own technology and educational institutes that foster technology in India. So after coming back, J.N. Tata wrote a letter to Vivekananda asking for his ideas about it, and they had exchange of letters. They are still preserved in IISc. That's how IISc is formed. So there's so much of Bengali Tata connection, and I think this is the crowd where I also belong to. And thank you so much, not only who are present here and everyone in the country who have poured a lot of messages to me when the bridge is inaugurated. I'm truly overwhelmed, very humbled by the affection and love poured to me. And I told that a bridge of this magnitude is not just possible with one person's contribution. There are millions of people who are behind this bridge. I still say the same thing. I'm just one of these thousands of people who have contributed. I'm fortunate to get an opportunity to work on this bridge. And I like my introduction, she said, I am the first engineer from a village. If I am standing here and talking to you because of the bridge. So the bridge has given me more than what I have given to the bridge. I strongly believe that, and thank the entire project and all of you for this. I will try to tell the technical story of Chenab Railway Bridge in simple words. So the bridge is the connection, train connection between Jammu and Srinagar. We didn't have a train between Jammu and Srinagar. It was a 127-year-old dream of India. Maharaj of Jammu and Kashmir was very keen on connecting Jammu and Srinagar by train, but because of complex geology and difficult terrain, this dream was not materialized until very recent times. And many governments changed. Maybe around 2002, the government of India has declared this as a national project. The Udhampur-Srinagar-Baramulla Rail Connect, a bigger plan where the entire Jammu Kashmir will be connected with the rest of the country. So Kashmir to Kanyakumari connect will be complete by train. That was the plan. And if you look at the picture what I am showing here, this is a civil engineering marvel. All of us the country is proud of this project because clouds are below the bridge. So this is the project where civil engineering meets clouds. That's what we call it. So the Udhampur-Srinagar-Baramulla link project connects Udhampur to Katra, where we have the Vaishno Devi shrine, and then it goes to Banihal, and then it goes to Srinagar, and then after that it connects Baramulla as well. So all other segments, Baramulla, Banihal, and then Jammu, Udhampur, all were connected except this part, which is very, very tricky, the Chenab railway bridge, which completed very recently. This is already shown in the video. Why this bridge is very difficult, very complex to construct. We are dreaming of connecting two hills, and there's a river flowing between, and there is almost half a kilometer of the arch which is not supported. If you see, the half-kilometer arch is completely unsupported, and the total bridge length is 1.3 kilometers. Bridge is at a height of 359 meters, 35 meters taller than the Eiffel Tower. If you stand on the deck, the wind can be blowing at a speed of 220 kilometers per hour. So we were talking about lateral stresses. Now we can imagine what amount of lateral stress at 220 kilometers per hour wind will pose on the bridge. And we are trying to build foundations, support for this bridge on slopes which are very steep. And we are talking about Himalayas. This bridge is in Jammu, which is lower Himalayas. With extremely difficult geology, so you are going to make cuts to put the foundations there. This is the reason the bridge took longer time than it was expected to be completed. So my involvement in Chenab Bridge started in 2005. Maybe around late 2004, end of 2004, railways have contacted Indian Institute of Science. The bridge belongs to Northern Railways. Konkan Railways is the execution partner because they are bridge experts. And then the bid was won by Afcons, a construction company. In 2004, end of 2004, they have come to IISc and had a discussion on involving IISc for the planning, design, and construction of this bridge. And I and my other colleague, Professor T.G. Sitaram, both of us were involved in the initial stages of the project. We were rock engineering experts. In later stages, he has moved out, and I continued in the project for 17 long years until its completion in 2022. So this picture was taken during the first visit. When I look back, this is a nostalgic journey. You know, going to those hills was not an easy task. Today, you can book online a ticket from Katra to Srinagar and travel by train. But when I first went to the site, I had to go to Delhi and take another flight to Jammu, and then from Jammu to Katra, go by car, take Kalis, and then go to another village, and then from there, take a boat, go in the Chenab River, and then reach the foothill and climb the hill. This was the first journey, I still remember. And those hills are not conducive for human living. There are no people living there. There are no facilities for people to live there. So we were living in camps when we are doing initial investigations. And extremely difficult terrain. This river flows into Pakistan. So it's a very sensitive region. Any small change to the river can be a political turmoil. So you don't want to disturb the river as well. And you don't want to disturb the hills as well. So the first impression when we climbed the hill was this. These hills are very steep, the peaks are extremely pointed, and very complex geology because of that, the terrain itself. Himalayas, younger dynamic mountain range. So at that point of time, it looked incredibly impossible to construct a bridge connecting two steep hills. That was the first impression. But then, we are civil engineers, we don't give up. You tell anything, we say that possible. You ask me to build this bridge in moon, we will say possible, right? Only thing is you need to evolve technology over time. It might take some time, but at the end, most of the times we are successful. This is how we have marked foundations on those slopes. Very, very primitive ways of marking the foundations. And then, first task was making approach roads, because there is no road, how to climb the hills. This was a big task. When you are making road, you are making cuts into the slope. Whenever you are making a cut, you might increase instability in the already unstable slope. Any extra cut, you cannot rebuild it because it is a natural slope and you use any other material, you cannot integrate with the original slope. So we had to follow the contours carefully. A digital elevation model was developed. All points X, Y, Z coordinates were mapped. And then carefully following the contours, these very kacha roads were initially made. And you can imagine how the travel on these roads used to be. When I am traveling on these roads, I don't see the end. I don't know whether I'm taking a right turn, left turn. I only see sky and valley. So I'm not sure whether I'm taking a turn or going into the valley. Some of the construction equipment were also fell into the valley and got smashed in the initial days. Anything that falls from that height it will not have any traces. So that was the kind of situation. And during my third visit, we just escaped a big landslide in a whisker. So these are kind of risks all civil engineers take when you are interested in doing a field job. I can sit at home and I can do my calculations and publish my papers. But the amount of satisfaction I get when I go to the field and look at these kind of things and get involved in these kind of projects is, I cannot measure the kind of satisfaction you get. Coming to the difficult part, the most difficult part is we are building something in Himalayas. Himalayas are very young, active mountain range. My friend Damodar Maiti has shown you the plate tectonic map where you have convergent, divergent plate boundaries. So this is a very active convergent plate boundary. The formation of Himalayas itself is a tectonic activity. The Indian plate was very far from the Eurasian plate, and there was a huge ocean which was separating those plates called Tethys Ocean. And Indian plate was moving at a speed of almost 10 centimeters per year, and about 10 million years ago it has hit the Eurasian plate, and the collision is the reason for the formation of Himalayas. And even today, Indian plate is moving at a rate of 5 centimeters per year in northeast direction. That means by the end of the design life of this bridge, the plate is already moved by 5 meters. So we are talking about extremely dynamic, seismically active tectonic plates, and we are trying to make a bridge which has to withstand these earthquake forces. One more challenge is, since this is a dolomitic rock, see the rocks in that region are primarily dolomitic, a form of limestone. They are chemically active. And whenever there is rain, the atmospheric carbon can become a carbonic acid and dissolve part of these rocks. That is why in dolomitic rocks you have very clear caves. Like we used to hear the stories of our rishis going inside and doing meditation. We have literally seen many such caves and open joints in the rocks. So how to fill these joints, how to make support to the foundations was another big challenge. There are different types of joints I am showing you here. I'm not going into the technical details, but all kinds of geological, morphological differences, different types of discontinuities, joints, weathered rock regions, sheared zones, everything was literally present at the site. Now in this kind of rocks, we have different types of failures possible. I have summarized in this small picture. I will tell you in brief. If you have, these joints are inherently formed because of formation of the rock itself, because the magma is coming out of, there is a subducting zone which is going below, and that magma comes out and forms these layers of rock. And because of that formation and the time of formation, there will be so much of layering that happens. And all these joints are in sets. There is no single joint. Usually they are in sets. And their inclination, the kind of material between the joint and their properties, everything can be different. Based on that, if there is one joint set which is making the part of slope fall into the valley, we call it sliding failure. And if there are two joint sets which are intersecting with each other and making the wedge fall into the valley, we call it wedge failure. And if the rock is completely fragmented and it behaves like soil rather than rock, then you can have a global landslide kind of failure. If there are parallel joint sets which are available at the site, then you can, sorry for this. Oh God. How to go back? This one? Okay. So when you have parallel joints, you can have a toppling kind of failure. Now, to start with, this was the kind of data that we generated at the site. The first one is we have a digital elevation model, which I already explained. Then we have seismology data, which gives you the earthquake signal, time versus acceleration history. This was developed by IIT Roorkee, but I cannot directly use this data into the design. Then we have borehole data. A set of borehole data is given by RITES, the part of railways itself. And there are more confirmatory boreholes done by Afghans. And some boreholes are almost a kilometer deep. So you have samples from these boreholes, you have different kinds of features, borehole data, all that is there. And then you have joint data. Some geologists were working day and night at the site, mapping the joints. We have how many joints are there, what is their spacing. The spacing is very close at some points. It is almost like 10 centimeters close, the joint sets. And then you also have lithology data, which gives you the properties of the rocks, their physical features, morphology, and other details. And then National Institute of Rock Mechanics has given the tomography data. They have done electric resistivity test, where you send electric signal into the rock. Based on the resistivity offered by different layers, you can recreate the subsurface, where you have a void, where you have high density, where you have low density. All that data is given. Now, you have to integrate all this big data when we are doing the analysis of slope stability or foundation design. These are my specific contributions to this project. Number one is, I have developed the slope profiles, how you need to make cuts, what kind of heights you need to have slope sections. Then geological and geotechnical investigations at the site, and then slope stability analysis, excavation scheme, and design of foundations on the slope, design of slope support systems, and design and construction methodology, and geotechnical analysis when arch is being erected, construction stage analysis monitoring, finally instrumentation and long-term stability measures. My 17 years contribution is summarized in these 10 points here. So this is how I have developed the initial slope profiles. This is taken directly from my computer, an Excel sheet. When I look back, I understand how immature I was when the start of this project, because my knowledge on rock engineering is from the books and then kind of exercises what I did during my postdoctoral fellowship at IISc. But this is evolved over the time. I was thinking that the first picture, if you see carefully, I was thinking that we can cut the rock like just below the foundations, deep cuts and put the foundation. Or you just follow the slope and make cuts and put foundations. But I realized that these kind of solutions are not possible in real life, because you cannot make such deep cuts in rocks. It becomes very unstable. And also you can't move construction equipment to make such kind of cuts. So the Indian Railway Services has excellent people in their team. And I had the opportunity and luck to discuss and deliberate with many of these people in railways who have profound knowledge on these aspects, and I have learned over the time. Finally, the last profile with the discussions with railways was finalized. That's what we went ahead. These are some geological details. And we made small tunnels to go inside and map the joint sets. During this time, there's a continuous work happening at the site. We need to map all the joint sets on both the slopes. And also small pits were made near the foundation locations. There also joint mapping is done. And finally, we found 4 different joint sets are available, J1, J2, J3, J4. Now these are like spacing, different orientations. All joint parameters are mapped now. All geological data, geological logs are available with me. Now, going forward, I do the kinematic analysis. I am not going to the technical details. If someone is interested, they can read my papers or come back to me. This is little complex. What we do is, we take the earth as a sphere and put all the joints on the face of the earth in a 2-dimensional way, taking the longitude and latitude, if you remember your geography, right? And that's how we put the joints. And with respect to the strength of the rock is represented by a central circle, what you are seeing. That is, represents the friction and cohesion of the rock. If your rock joint is falling outside the friction cone, the central circle, your slope is stable. If it is falling within the friction cone, you have instability. That is causing sliding. And whatever sliding I have predicted on the paper, it was actually seen in the field. That is the confidence. We gain confidence from this kind of simple exercises. And if two joint sets are intersecting and the intersecting point is falling within the friction cone, then you have a failure. That is a wedge failure which you can see in the field. Toppling failure also. Incidentally, at the field, toppling and sliding were not a big problem because the main problem, main instability was wedge failure. There are crisscross joints which are intersecting and forming wedges. Huge block of rock are ready to fall into the valley. See, you can say that the Himalayas and these kind of slopes are standing for thousands of years. What new instability you can expect? So the instability may not be under static condition, but when you are going to cut the slopes and when you are, there can be a possibility of an earthquake of higher magnitude at the bridge side, that will cause the instability. Otherwise, these slopes are very safe. So yeah, when I talk about slope, you must be seeing in the two-dimensional way, there is one slope, one slope. No, these are three-dimensional slopes. You have to cut on all three sides for both slopes. So that is the challenge. So we followed a top-down approach, started from top, because if you do something from bottom and then go top, any disturbance from the top falling onto the down would be problem. So start from top and slowly move to the downward sections. This is the aerial view of the cuts made on the slopes. And people who are very familiar with blasting, we civil engineers are experts in blasting. If anything has to be cut, we just put explosive and we can blast. But in case of a slope like this, blasting indiscriminately can be a serious problem, because if you cut anything extra or if you cause instability, it is going to be a big problem for the slope. So we followed this pre-splitting method. Pre-splitting is you have this carefully placed, planned, designed boreholes into which you put the explosive, and then you cut that part. When you make these pre-splitting boreholes, you make a very clean cut, unlike when you do indiscriminate blasting or normal blasting. Once you make that cut, the closer portion will be carefully cut using controlled blasting. That is what is done. And very interesting picture I'm showing you here. If your slope has several sections, if your section which you need to cut is very close to the slope profile, then you do the pre-splitting, remove that part and do the control blasting. Before you move to the next section down, you first stabilize the top portion. So any explosion below will not cause problem to the top section. That's how it, and then when you go down, the section which is away from the slope is cut with normal blasting. Then the next section close to the slope is pre-split. Then you do the control blasting, put the rock anchors, then move to the downward slope. This is how it is slowly progressed. What I am showing you here is a 7-meter slope, and we are talking about 359 meters. So you can imagine how much of blasting, cutting, anchoring was done at the slopes. Another issue here is if you are blasting and you are creating so much of dump, debris, if it falls into the river, it causes silting of the river. You don't want that. And that is why dump yards are created. And it is very easy on plains, like, I mean, you have a plain land, you can easily carry the dump material. But on slopes like this, at that altitude, with one-way kind of a movement, it was very difficult. But carefully, no debris was allowed to fall into the river. And then the rock anchors part. Rock anchors are for stabilizing the slope. Whenever we are doing the cutting, then you stabilize the rock against the wedge failures I talked about. The wedges were huge. Whenever there is a wedge, there is a kind of disturbing force, and you need to resist that disturbing force using rock anchors. And pull-out tests are done, several of them, to understand the pull-out capacity of these anchors. And shotcreting is done, 100 mm thick shotcreting with steel fiber reinforcement is done on these slopes. So this is how the rock bolts are designed. You have a wedge. And in any slope stability, we have something called factor of safety. It is derived as resisting force divided by disturbing force. In this case, disturbing forces are earthquake forces, weight of the wedge which is falling, and then any other surcharge in terms of foundation load that is coming. So all these forces are trying to pull this wedge into the valley, whereas we are trying to put steel anchors to resist these forces. That's how the wedge failure is arrested. So this is a simple slope section where you can see these stitched rock anchors, and you can see the anchor plates as well. A close-up view looks like this, which is like slope stabilization for a small section. This kind of thing is done for all slope sections which are cut into the slope. These are done in a zigzag way, so you get maximum resistance to the wedge failure. You can imagine the kind of excavation. It is more than 3 lakh meter cube of excavation is done, and rock bolting was almost 67,000 meter, and shotcreting was more than 76,000 meters square. This is the kind of magnitude of the thing. Now a bigger challenge happened. When we designed the foundations or the slope stability support measures, we have taken parameters which are mapped on the surface, right, on the rock original slope surface. But as we had to excavate this for cutting, we went almost 20 meters deep into the rock. By the time all rock parameters changed, you have a different type of rock, you have a different orientation of joints. Some joints vanished, new joints appeared. The material which is in between joints is new now. Persistence of joints changed. So this was a big problem. So this is the reason we adopted a design as you go approach. If you had a fixed design, this kind of surprises when you encounter, it would be extremely difficult to change your design. So in the entire Chenab project, the only constant parameters are the shape of the bridge and the number of piers. Other than that, everything, the location, dimensions, and depth of the foundations, depth of the arch, everything were evolved with time based on the surprises that we encountered. That is why this design as you go approach is extremely important for bigger civil engineering projects where you are talking about kilometers of distance. So this table summarizes how big the changes were. Some places you have 36 degrees change in the dipping observed in case of joints. Now coming to the foundation design, this is my favorite quote of Carl Terzaghi, who says that since foundations are inside the ground, they are buried inside the ground, often the glory is only attached to the structural part and foundations are treated like stepchildren. And their acts of revenge for this lack of attention can be very embarrassing. It's a very, very true statement, because most of the times you worry about how my house look outside, how my functionality, how my comfort, everything. If your foundations are weak, whatever, how beautiful you are building your structure, it is going to fail. So with this, we gave a lot of importance to the foundation design because we are carrying a lifeline. You are carrying a train on the foundation. So extremely careful, precise design was done. And this is how, when we are trying to get the bearing capacity, the cores were looking like this, extremely fragmented. There is no connection. If you understand what is rock quality designation, that is the kind of connectivity between rock, this is poor to fair kind of a rock. So before you put foundations, our first task is connect these fragments to have a homogeneous foundation. So we have 3 sets of properties given for this rock. One was given by railways, one was given by IIT Delhi, and one we ourselves done the testing and we evolved. But in case of railways, whenever you have these 3 sets, what they will tell is use all the 3 sets and then come up with worst case scenario. That's what we did. So for the geotechnical investigations to understand the bearing capacity, we cannot rely on one method in such cases. We need to understand the bearing capacity using multiple methods, multiple analysis, and use the least possible value. So at the site, we have conducted direct shear tests from which you get C5 parameters and you get the allowable bearing pressure. And we did the actual cyclic plate load tests, and then got the bearing capacity from that as well. And then we also did non-destructive testing, multi-channel analysis of surface waves, where we send the sound waves, ultrasonic waves into the ground, and based on the reflection time of these waves, we can get the density and shear modulus. Once you have shear modulus, you can calculate what is the bearing capacity. This was also done. And dilatometer, just my colleague has explained. So those tests were also done at the site, inside the tunnels what we made. And using this also we could get the bearing capacity. And then tomography, electric resistivity tomography also we did, and from that also we got the bearing capacity. And apart from that, we also estimated the bearing capacity from the unconfined compressive strength test. Also joint factor model proposed by Professor Ramurthy of IIT Delhi. Many analytical equations. Finally taken the least possible bearing capacity, which is 100 tons per meter square, into the design. And so initial foundations and final foundations, when we started this project, we had like designed based on what is the available data, the big data. But then over the time, when the properties are evolved, when we could do the tests, everything changed. The size of the foundation changed, and its depth changed, type of foundation changed. So these changes are summarized. I've recently published a paper on this topic, design as you go approach, in case of the case study of Chenab Bridge, where I have summarized how the things are evolved over the time. Now the slope stability analysis, we did 2D, 3D analysis using FLAC 2D and FLAC 3D of Itasca to understand that whatever support designs we are making are strong enough to support all kinds of loads, including earthquake loads. So if you remember, the first picture is what is IIT Roorkee has given. Now Railways has changed the strategy. They said, like, this is small earthquake. This earthquake is the maximum credible earthquake that is possible at the site. But what if there's a bigger earthquake that might happen at the site? So the original earthquake, see, we cannot directly correlate it to magnitude, but in very crude terms, the first one represents a magnitude of 7. So Railway says now you have to design the bridge for a magnitude 8 earthquake. So that's very simple to say 7 to 8 because it's just one number. But the energy difference between 7 magnitude and 8 magnitude is almost 32 times. That means you need to increase your support system to withstand 32 times more earthquake forces. So that changed a lot of things. We have done so much of analysis for maximum credible earthquake. We have a factor of safety of 1, design basis earthquake factor of safety of 1.2, and static conditions 1.5. These were the factors of safety mandated by the railways for withstanding the synthesized earthquake which I have developed. To develop this synthesized earthquake, the original vibration developed by Roorkee is kept the same, and only the amplitudes are increased at every frequency level. That's how we reached a peak horizontal acceleration of 0.36 g, which was originally 0.31 g. And these are the kind of wedges I was talking about. So earthquake force can happen in any direction. So we have taken all possible scenarios of any direction which can happen and taken the worst case scenario and designed the support system for that. Once the slope support system is in place, we have also done the further numerical analysis to compare our factors of safety and the overall deformations, whether they are within the range or not. Now to construct the foundations on slope, whenever we have to, I showed you there is fragmented rock, then the best solution would be to do grouting. So when you do grouting, typically in a normal ground, our foundation can have a pressure bulb extending up to twice the breadth of the footing. We take it as effective depth of pressure bulb. But in anisotropic rock like this, completely fragmented rock, the pressure bulb can go up to 4 to 5 times the breadth of the footing. And it need not be circular, it can be elliptical. And if you send the pressure grout into the subsurface, it can heave up because there is volume change. Now you need to do this very carefully. So consolidation grouting with very low pressure was decided, and we started working on it. And there was another big surprise. 50,000 bags of cement is gone into the rock. We cannot find any trace of this grout where it is gone, because there are so many open joints, interconnected network of joints, and whatever you are putting, it is just vanishing into some place. We can't even know where it is for almost 2 months. This is a simple problem, but we were not able to figure out how to solve this. So we were working on like how to resolve this. So very simple engineering intuitive solution we figured out. We mixed color into the grout. And then we mapped where the color is coming out. So we found the location where the color is coming out, how much time it is taking to exit from entry point. Based on that, we have reconstructed the joint network inside the rock slope and did several trials to confirm this is the path it is taking. And then we have carefully designed the mix of grout using sodium silicate to set exactly where we want. So this solution looked very simple, but it worked. It saved crores of money to the project. And the grouting is always done at the outer holes first, and then you move inside. When you do grout the outer holes, you are creating a barrier, and then the inner hole grouting will be much simpler. So this kind of grouting is done, and after that we have taken course and we realized that cement is gone between the rocks. And careful look, you can see that rock fragments have cement layers in between. We have conducted uncompressive strength tests on many rock cores to confirm that the rock grout is set and it is giving adequate compressive strength. And we also did the non-destructive testing, multi-channel analysis of surface waves and electric resistivity to make sure that the subsurface, which has shown a lot of voids before, is now homogeneous and it is nicely grouted. If you can look at the size of the foundation here, that will give you the perspective why I am telling so much story about this, right? The foundation is of 49 meters length and 35 meters width and almost 47-meter height at a 20 meters depth inside the rock. So if you stand near the foundation, you won't be able to see the full picture. You need to go a few kilometers far to see the full foundation and take a picture of it. That is the size of the foundation. This is one foundation, one arch foundation. Now that the arch foundations are ready, we started building this arch. Arch erection was very, very important part. It took lesser time, but it's one of the major tasks here because you will not be able to put any cable crane on the river. So we erected 2 cable cranes on both sides. These are the world's highest or tallest cable cranes, 120 meters tall. Each one can take 20-ton load, and together they can work in tandem and take 35 tons of load. So these cable cranes are working together to bring arch elements and assemble it. When you are assembling these arch elements, since arch is a very effective structure to distribute the loads, but if it is effective only when it is complete. But when it is in assembling stage, it will have very unstable structure. So to give stability to these arch elements which are assembled together, we had to put cable ties, cable stays to put them or make them stay at one place. So these cable stays again need support. So we had to use foundations to support these cable stays. When you use cable stays to support the foundation, it is subjected to traction again. The foundation will be pulled up. To provide support to the foundations, again we had to put pre-stressed anchors to the foundation. And this support is not permanent because the cable stays keep changing their location based on the arch. If it is coming up slowly, you need to use a different foundation for support. So this was a kind of a challenging task. This is arch erection stage analysis for the foundations. And this is slowly from both sides, the arch has come up. This is called golden joint. When both of them come together, they don't naturally come and join. You need to make engineering adjustments for them to join. So the golden joint, when it is completed, so all of us were so relieved. This is when you know that the bridge is complete almost, because the deck is a simpler task. There's a huge celebration. It was an Independence Day, and then on top of the deck, there is this flag which was taken one side to other side on the bridge at that point of time. After that, this incremental launching of superstructure. First time Indian Railways has done this incremental launch of superstructure on both circular and transition curves. So these deck elements were very naturally transported on the approach roads, and they are brought and they are assembled, and the superstructure is ready. So these are some pictures of progress. So how a natural slope was made into this bridge. And there were some ledge distance issues which I identified maybe in 2016 or sometime, because we wanted a 5-meter distance to be on safe side from the slope, but that was slowly little bit eroded. So at that point of time, they were protected with the retaining wall is constructed. Railways has approved this. And wherever we have natural debris or overburden, I have designed cladding walls and gabion walls. And wherever there is a natural water flow, kind of an nullas formed, there also these cladding walls with gabions were designed and they are nicely placed. These are some unique features of the railway, Chenab railway bridge, which make it most wonderful structure. It has a design period of 120 years. It can withstand magnitude 8 earthquake. It is blast proof. DRDO has worked on making this blast proof because it is very close to line of control. And it can withstand climate change, minus 10 degrees to 40 degrees centigrade temperature, the materials can withstand. They are custom made materials. And double corrosion protected steel, like whenever you have these pre-stressed rock anchors, when they get corroded, you have loss of material which can release the pre-stress. So they need continuous maintenance. All the arrangements for maintenance of these pre-stressed bars are taken care at the site. And even if you remove one pier or one critical section of the arch, you can still run the train on the bridge at a low speed. That is the beauty of this bridge. And these are the cable cranes I was talking about. And this is the drone view of the golden joint. And first time when I went to left side, if I had to go to the right side, I have to climb down the hill and then go to the other side and then climb up. So it used to take 2 days even in the car. After the completion of the deck, I could walk in few minutes from one side to the other side, which gave me goosebumps. This is what we have worked for, right? So this is how in winter the bridge looks like. There's a video, but they've already played video, so I'm not going into it. So this is when Vande Bharat train ran. PM Narendra Modi ji has inaugurated it in June. And that moment gave so much satisfaction to everyone, every single person involved in this design. Thank you so much.
Truly inspiring lady, we all know. And we are really privileged. This is the love that we wanted to present to you, ma'am. Thank you so much for coming over here. Thank you so much for joining with us.